Welcome back class for the lecture on local search, and last time we discussed the basics of the local search methods and some of the problems that can be solved with this. Now this time we will discuss the practical different types of local search methods and practically how they work. So the local search algorithms we will be dealing with will be the hill climbing, simulated annealing, and Tabu search, and then we will go to the next method of population-based search algorithms. So these ones you see over here, these three, they are the local search methods and that we already have studied. The method we have seen, which is very simple. You randomly select a starting point and you search locally in the nearby areas until you are satisfied, or you have to reset or you. So the first method we will see is the hill climbing. So hill climbing is a method just like some person is trying to climb the mountain, Mount Everest, a very high mountain, in a very thick fog and with amnesia. Amnesia means that he don't have any memory. Okay, amnesia is type of disease where the patient he don't remember anything. So there is so thick fog that the person can't see what is next or what is around. Okay, or he can't know anything that he's going up or down. And also amnesia means that he don't know what he did in the past. So he was coming up, or he was coming from the top to the bottom, or he was coming from down to the up. So hill climbing search algorithm, we also call it like a greedy algorithm for local searches. So it's greedy local search. What we try to do over here is we use a loop that continually moves in the direction of increasing values. So for example, if I am standing at this point over here, then I will check the surroundings, all the points in the surroundings, all the states in the surroundings, and I will only select that state which will give me more advantage. So you see, this is like the greedy approach we have seen before. So we try to get more advantage, we try to do more greed. And again, like greedy search, it has got some disadvantages. We terminate in this case when we reach at a point which is a peak and there are no neighbors that has a higher value. So for example, when we reach this point here, we stop. There is no neighbor that is higher than this value. So this, as you remember, if we want to maximize, this is our local maximum. So again, same thing as we have seen previously. For the greedy search, the main problem is that you will be stuck with a bad solution. So you see over here in this case, you come at this point and you cannot go to that point over there, the highest peak, because that highest peak comes after this low level, and greedy search will be stuck at this level over here. So this approach is called hill climbing, and you can see this is a bad approach. Another name for greedy search, you can say an exam question can be, another name for hill climbing is greedy local search. So overall, it gives us you see how it works now. So you see on the x-axis you have the different states, so different possibilities, different conditions, and on the y-axis you have the evaluation of the state, means that this state is good or not. So greedy search, it will try and keep on going, keep on improving, and as long as it is getting some good results from the next state, it will keep on selecting that state. Okay, and there will be a point that comes that is the maximum for that state, and you will stop over there. Okay, so you start with the hill climbing. This is it. So this is a typical local search method that you have seen. You start with some initial state, this green one, and you keep on improving. You keep on improving until you see using some local transformations, little bit of transformation or little bit of changes. Perturbation means changes. So little bit of changes, you keep on doing it until you see that you have got some better result or until the time is over. So here is the algorithm given. This is a small function given. This is just to give you an idea, so don't be scared of this. Over here you see the function hill climbing. So you have a problem and it will try to give you a solution state for this problem, the best answer or best state, only one state, not the path. Okay, remember important point, local search, we don't deal with path. It is not like the Google Maps where you are interested in the whole path. So you have the input, a problem, and you have two variables. You define current variable and next variable that represents a state or a node. So what you do is that you start by making the current variable as a random state, a random initial state. So that's what you did in the last slide. You see, you start with this random state, and then what you do is you keep on looping inside a loop, and you select the next node. So next variable will contain a node that has a highest value successor of the current. So that has a value that is more than the current. So you try to check it over here. The value of the next, it is less than the value of current, then you keep the current. Else you will swap the current with the next. Okay. So here it is. Initially when you start, your current is this one. Then when you see, try to find out in the neighbors if there is next. So you select any neighbor, any next. So this is your next, and this is maybe another next over here. So maybe I need to change color. So there is another next over here. So you will compare the next node with the current node. If this next node, its value is less than the current node, you will discard it. Means you don't approve. Then you go to the next one. So here is another next node, and this one over here, you try to compare its value with the current node, and let's say its value is better than the current node, then you will replace the C with N. So C now points to this node. So this is how it works. It will keep on doing this thing until you are satisfied with the result or until the time is over. This is hill climbing. Here is the example on the 8 queen problem. So remember, in the 8 queen you have got 8 columns, and each column has got one queen that you can place up or down in that column, anywhere you can put it. And what you need to do is that you want to reduce the number of queens that are in a straight line with another queen. They are in the attacking position. Okay. So for example, if you see, there are 8, so a state will have 8 queens on the board. So overall we have 8 queens, and the neighborhood of a state of all states generated by moving a single queen to another state in the same column. How many states you have got? For example, if you consider this column, okay, now in this column you have got this queen at a present location. How many possible states you can move this queen to? So if you see, other than its current location, because current location is already queen is there. Now the next state that you can get is you can move it to any other location. How many of them are there? 7. Okay. So like this, every queen has got 7 possibilities. So in total we have got 56 next states for one state. So this is one condition, one state, it has 56 possibilities that we can choose from. Clear? So hill climbing, you select a random state, that is the initial state, and then you select one of the neighbors that is better. So let's say initially you have the h value which is equal to 17. So in this solution, 17, there are 17 attacks that are possible between the queens. Okay, so that is huge number, a lot of queens attacking. So h over here represents the objective function, which is equal to, which is basically the number of pair of queens that attack each other in state S. Okay, so 17 of them are attacking each other. So if you move it to another state, the best one that I can see over here, you move these queens to one of these pieces, then you can get 12. You can get the attacks, you can reduce it to 12, from 17 to 12. So this is how hill climbing works. This is the typical, you can say, the local search that we already studied before. That is exactly same as this hill climbing. Local search was a general idea that you saw previously. Here hill climbing is one particular example, one particular algorithm. Okay. In the future we will see, you see, there are many problems, many drawbacks in this approach. We will see improvements also. So next what happens is, the best that we can get from this starting point is when you have only one attacking queen. So this is the final solution, the local minimum. So we want to minimize over here the number of attacks. The best that we can get with this starting point, it is 1. So remember, based on your starting, so if you are, for example, starting from here and you want to maximize, you will reach over here. You start from here, you can reach the global maximum. And for the minimum also, it is the same story. So if you start from here, the minimum that you can get is this value. You start from here or here or here, anywhere, or until here. So you will reach this point minimum. So that is it over here. For this set of states, the minimum, the local minimum is 1. Clear? So in hill climbing, this is how we define the neighborhood. So neighborhood of a state, it is all the states that can be generated by moving the queens in possible states in a column. So there are 56 neighbors for one state. So what are the drawbacks for hill climbing that I already discussed? Local maximum and minimum problems. The local search can get stuck on a local maximum and minimum. This is what I already discussed previously. And you will not be able to find the best or optimal solution. Okay. So you start from here. You keep on improving. You are stuck over here, local maximum. Okay. You can never reach global maximum. And sometimes there is a huge difference between global and local maximum. Okay. You cannot improve because of this approach, which is not so good. We will see some other approaches that are more better than this. So what is the cure? How to solve it? One other solution that we can apply on this approach is we try to do random restart. These approaches we will see in the future versions. One is to do the random restart. So instead of you are stuck over here, try to restart somewhere else randomly. So randomly you restart here. Maybe this time you will get the local maximum, global maximum. And it is only good, this approach, for few local maximum. If you have got too many of those maximum, if your state space has got 10 local maximum and one of them is the global maximum, which is very big, and others are all very small, so in that case you have more chances. Let's say you have here many mountains, so even if you start randomly, you have more chances that all the time you will be stuck in one of the local maximum mountains. Global maximum reaching, it is more difficult. Clear? So here it is hill climbing. What we do, current solution, green one is the current and red one is the proposed future solution. So so you can say this is the current node and this is the next node, red one. So next node we only select. So remember, don't confuse this thing with maximum and minimum. Sometimes we want to maximize, sometimes we want to minimize. Over here in this approach, for now we are focusing, we want to minimize. That's why you see the value of current node is decreasing. Okay, so minimize, and we want to go to the minimum. Ideally, the best we can do is we want to reach the global minimum. But there are two other minimums, local minimums, that are possible. So current solution and the next node, it will keep on improving, and you see over here, it will reach the local minimum and it will be stuck. There is no other solution. So typical exam question, hill climbing, it will give you the best solution it will give you is local minimum. Okay, so the issues is the goal is to find the global minimum, which is not so possible with your simple hill climbing search. So how to avoid the local optima, that's a big question. How to avoid this local optimum, and when you should stop searching for the algorithm for the best point. You keep on searching, when you will stop. Okay, so these are the issues that are with hill climbing. You can do nothing. Here is another example. This time we want to go for the maximum, not the minimum. So we are already at this point. We cannot go further from this location. And you see, if we could have done a little bit of compromise, if we could go a little bit down, then we had more chances to go up to the maximum, global maximum. Secondly, when you will reach over here, when you should stop, that's another question. And this is the big problem that I discussed here. When you are looking for the global maximum, sometimes you should allow to climb downhill. Allow a little bit of going down, and that's the issue with the hill climbing. There is no solution in this approach. For that purpose, we give a little bit of modification in hill climbing. This modification we call it stochastic hill climbing. Stochastic, you know the word stochastic means it's the opposite of deterministic. So stochastic means randomness. So random hill climbing, it's also called simulated annealing. And what it does, the key idea is that you escape the local maximum, okay, by allowing some bad moves but gradually decreasing their frequency of bad moves. Okay, so what we do is I will go and first show you the example and then we will come back to read the theory. Let's go to the example, this one. So simulated annealing or stochastic hill climbing, you start with your initial state, you keep on improving this state, stimulated annealing, you keep record of your best value, but you allow to randomly select different states in the neighborhood. Maybe their value is bad, you allow it. So you keep track of the best value and you allow to go a little bit away from the best value. Search in the neighborhood, even the values are not so good. The state evaluation is not so good, still you allow to select it. So you keep on doing this for some time and hopefully sometime later we get a value that is better than our current value. So you see the difference? When the value of the node becomes better than the already best value, we update it and we keep on doing this until we are done, until the time is over and we stop and hopefully, again the word used is hopefully. There is no guarantee in these methods. So hopefully we stop with the global minimum in this case. So this is simulated annealing. Now why we call it annealing? Annealing is basically the word that comes, so let me go back. So annealing is a word that comes from metallurgy, the study of metals. Okay. So annealing is basically a concept that comes from physics, where, for example, if you want to make some metal, for example steel, and also for glass, the window glass, if you want to make them more stronger, okay, you want to make it strong, what you do is that normally in normal temperature the steel and glass will be strong, but what you do is that before you make it in the normal temperature, what you do is that you heat the metal and the glass, you heat it a lot and then allow it to cool down slowly. So this method in physics, it's called, in metallurgy it's called annealing. Heat it up and then allow it to cool down, and when you do this, what happens is that the glass molecules or the metal molecules, they align themselves in a crystal structure. So when they align themselves in a crystal structure, they become more stronger, and overall their strength is increased as compared to the previous state. So in metallurgy, annealing is the physical process used to temper or harden the metals or glass. The purpose is to make the metal or the glass harder. And how they do this? They do this by heating them to a high temperature and then gradually cooling it down. And this allows the metal to coalesce, means to align itself into a low energy crystalline state. So what does this sentence mean is that the molecules of that metal or the glass, they align themselves in a crystal structure so that they have more strength. So heating, overall the important step for us is heating, then slowly cooling down a substance to obtain a strong crystalline structure, that is called annealing. So what we do over here is we try to do the same annealing in a simulated version, simulation of the annealing. So what we do over here is simulating annealing combines the hill climbing. So you take the previous approach and you combine it with random walk. So for example, you are moving around, you are going down the mountain, you want to find the lowest point, and you allow to do a little bit of random walking or movement in some way that will yield both efficiency and completeness. So you allow to move down the mountain, to go down, and when you reach a local minimum, still you allow to move around or walk around in a hope that with time maybe I will reach some other minimum value. That is the idea of simulated annealing, that is taken from physics, and overall it is used in the circuit layout problems. For example, when in the old times in 1980s, now there are more advanced techniques, but in 1980s when the structures were created for computer hardware or television circuits, at that time they wanted to make the circuit path the shortest and most efficient, and for that purpose they used these methods. So let's go back and see the theory. So this is the idea: you escape the local minimum or maximum by allowing some bad moves, but you gradually decrease their frequency. Initially you take very big steps, later on, so initially, for example, here I show you, initially when you have reached this point, now initially you allow very big steps. for bad move. One step is this, maybe the other step is this here. But later on, when the time passes, now you start making the bad steps smaller. And as the time passes, they become more and more smaller. That's the meaning over there. Clear? So you take some uphill steps to escape the local minimum, and instead of picking the best move, it picks a random move, not the best. So it's not a greedy algorithm, it's not a greedy local search. So it picks a random move, and if the move improves the situation, we execute it. Otherwise, we move with some probability less than 1. We keep on looking in the neighborhood with some probability. This whole method has a physical resemblance with annealing process in physics that we have discussed. So you allow the liquid to gradually cool down until it freezes. So overall in this method, the heuristic value is the heuristic value means the calculation you want to make, the mere is about the energy, how much energy you provide, how much bigger steps you take, and you control the speed of convergence, how you will quickly go down the hill, how you will reach the lowest point. So this was the idea about simulated annealing. Leave these algorithms, we are not interested in these algorithms. So so leave this temperature and cooling schedule, leave this, but here it is important that in the beginning, at the start of this annealing process, you have bigger, that's what I showed previously, you take bigger steps, you are more aggressive so that you search better alternatives. But slowly you start taking smaller steps, you become conservative. Conservative means more restricted. Take smaller steps when time goes by. That's what we discussed previously. Initially you take big steps, you are more aggressive, and slowly you start making smaller changes. So this was the simulated annealing. And pause the video, go through these slides, and if you have questions in the group, ask these questions. So at the end, when the time passes by, hopefully simulated annealing will make us reach the global minimum that we desire. Okay. Now the next one that comes is called the Tabu Search. Tabu Search is also the version of hill climbing. So again, remember, hill climbing is the basic, like the basic local search. Then a little bit of improvement was stochastic hill climbing or simulated annealing. Then there is Tabu Search, which is another improvement. What is the improvement? Basically, if you remember here, we were searching, and in the search we go around, for example, different nodes. Okay, so we are going around and searching different places. There is one big problem. Practically, when it is happening, this node that we are currently in, there will be many other nodes that we are searching, for example, in a loop, repeating. So I search this location, sometimes later I search this, then I go next, then I come again, search this or this. A lot of energy is wasted, a lot of time is wasted in looking at the states that we have already seen, which is not good thing. Okay. So what we can do is we try to keep a small memory. If you remember at the start, I said that hill climbing is an approach where you are going to the Mount Everest. So let me go back. So if you remember hill climbing, we discussed over there that, where is it? Yes, this one. Hill climbing is the search algorithm that you are like climbing the Mount Everest, the highest mountain in the world, in a thick fog with amnesia. So you have a very thick fog, you can't see around, and you have a problem of keeping memory. You don't have any memory. You don't know that you are coming from down to up or you are coming from up to down. Okay, so we try to remove this drawback, amnesia, and let's try to keep a record of little bit of past. That is what we will do over here in Tabu Search. So what we try to do over here is hill climbing with small memory. So the word taboo itself in English, it means forbidden. Okay, so let me change it. So taboo means forbidden, mamnu. Okay, so taboo search means that it is avoiding to search those states that we have already seen. Those states are forbidden. They are mamnu because we have already seen them. We don't want to waste time on those states that we have seen in the past. So the basic idea of taboo search, it was described by a scientist Glover in 1986. I will come back to the meaning of this sentence. First, I will show you the approach. The overall approach is to avoid entrainment. Entrainment means the best word you can replace is circling. Okay. So the overall approach is to avoid circling in cycles. So circling in cycle means you keep on looping in the old states. You have already seen them and you keep on going back to those states. So you avoid circling in the older states by forbidding them, or you put a penalizing you put a penalty. You penalize the moves. For example, if it goes to such states, you put some fine. So penalizing the moves which take the solution in the next iteration to the points in the solution that were previously visited. Okay, so you don't allow your algorithm to go to that states that have been previously visited. Always the algorithm should go and look at new states. So overall, the taboo search is not so old. Glover, he attributes its origin around 1977. I don't think you need to memorize these dates. Okay. So how it works? Let me show you. First we see the demo and then we will come. So taboo search in action. You start with the best and you always keep track of the best. So green is the current node and red is the next node, and you keep track of the best. So best is a separate variable. Okay. So current and the next node, they keep on changing. So it changes randomly, as you have seen in the stochastic hill climbing. And the best you keep track separately. So this is important. You keep track separately for the best. And you keep on doing, and it is happening same thing as you have seen previously for the hill climbing. So stochastic hill climbing. So if you see simulated annealing, you were doing the same thing, but the important difference is that in the simulated annealing you had only one current node, you don't have any next node. But here in the taboo search, you have two nodes. So two nodes, and always you make sure that your next node, it is not any of the previous nodes. Okay. So when the next node, it is searching, this should not go back, because remember, it is searching randomly. The word used is random. So randomly it not only goes forward, maybe it can go and search this location, but it should not be inside the list of already visited nodes. That's important point. Clear? The rest of it is same as simulated annealing. No difference. So it keeps track of the best, but the only difference is it keeps track of the values or nodes that have been already visited. That's how it works. So let's go back now to the theory. So how it works, the Tabu search? You start with an initial feasible solution, okay, some solution that is valid but maybe a bad valid solution. You initialize the taboo list. There is a list that you keep track of, and you generate a subset of neighborhoods or the neighbor nodes and find the best solution from the generated ones. From the neighbors, so you generate a list of neighbors that are possible, which I can select. Okay. So for example, this is my current node and I have these neighbors that are possible, which I can select. Out of these neighbors, I will select the best neighbor. So let's say this is my best neighbor. So this had the value I want to minimize. This has 17 and this has 12. Okay. Now 12 is good. Okay. Now this is important point. Now if my current node is over here, let's say this is current, and my next node that comes out, one option is over here which is more costly, so current is maybe 17. Okay, and this option over here is 20, and there is another one over here, this is 12. Okay, now there is a problem. That's the Tabu search for that. 12, I have already explored this 12. I have already gone through that point. That was my point that is in the Tabu list, because I have already passed through this node. Okay, so 12 is an option, but I will not select this 12 because it is in my Tabu list. Okay, so I generated the subset of nodes in the neighborhood, and I find amongst these nodes, amongst these 5 nodes, I select the best one, and I will only move to that node if it is not in the Tabu list. Then I will accept it. Clear? So if this is in the Tabu list, then I will select the next one, which is for example 20, which is more costly, but I will select it for now. Remember, I will keep track of the best. Best is separate. Best is pointing to the 20. So best is something separate. I keep it separate. It is not changing. So I keep on repeating the third and fourth step, these steps, until I hope that it's finished. 3, 4, 5, I keep on repeating. So this is Tabu search, where you keep track of the list of nodes you have already explored in a hope not to waste time on the already visited states. Clear? So this is it. This is the Tabu search. Pause the video, go through these slides, go through this simulation, this animation, and if you have questions, ask in the group. So hopefully this searches the best global minimum for you. So these were the 3 algorithms we have discussed that were related to the local search. So we saw local search is a general name. Local search is a name given in general. Practically, local search is represented by hill climbing. Then a little bit of modification gave us stochastic hill climbing, second approach, and then the third one was not to waste time on the nodes that on the states that we have already seen. We use Tabu search. So these 3 were the local search methods. Next one that comes is a different approach, a little bit of difference. We call them the population based algorithms. These are also optimization algorithms, but they are based on population. What does it mean? We will see. Okay. So population based algorithms, the ones that we will see over here are beam search and genetic algorithms. Now remember, in this chapter, whatever we are studying, these are the advanced topics. These are the topics that are the current research areas. These are the state of the art for search algorithms. So these are some of the topics that are even currently people are writing papers, research papers, research articles on these methods and algorithms. So population based algorithms, first one we see is the beam search algorithm. So unlike the hill climbing method, or you can say the local search methods, we call the beam search method, we call it local beam search. Okay, here we keep track of k states rather than only one. Okay, so we don't depend only on one current state, we have some set of states, maybe 4 or 5 states. So that's why we call them population based methods, because we are selecting a little small population of the states. So here I will show you. Okay, here first again my method is to show you the demo how it works, and then we will come to the theory. So in the local beam search, what we do is we start with some population. So population number you define, it is defined by k, and in this case, for example, k is equal to 4. So you select 4 random points in the search space. Clear? So you select 4 random states from the overall search states. So all of them are randomly selected states, and for each state you map their cost. Okay, so you start. Remember, practically in the practical world, you don't have any idea about the structure of the state space. You don't know where it is going up or down. If you know already, then why you should search? You already know where is the minimum. Okay, so practically the line that you see over here, it's not known to you. So in the practical world, we are only knowing those state values that we have already explored. Okay, so we start the local beam search, and we do the we explore all of 4 of them separately. So you can say that it is just like your hill climbing, but here we have 4 samples and we do them in parallel. Okay, so you do this, but there is one difference. It is not exactly same as running the hill climbing 4 times in parallel. No, there is a difference. After the first step, what you do is that from the given, now how many states are there? Okay, 4? No, there are not 4 states. 4 of them are the next states, but practically you have now 8 states. 4 of them are the old, and the 4 of them are the new next states. Okay, so practically total you have 8 states. So out of these 8 states, you select the best 4. Okay, so the best 4, if you see, these 2 are selected because we are selecting the minimum values. So these 2 are the minimum from the other all of them, and then you select these 2 because they are lesser than this one. Okay, so you select these 4 values out of others, and others you discard. So you see the 3 current states were discarded, and one next state was discarded, and we select one of the current states because it has more it has less cost. It's more attractive option. So this is local beam search. It is not same as running the hill climbing 4 instances in parallel, because here we are selecting the best 4 options at the end. So you select them, and then we start again, do some improvement in the local. So you see over here, this red, it is the improvement of this one, and this red is the improvement of this green one. Okay, so we select the improvement. So remember, we only for each current state we check all the neighbors, and we only select the one that is improvement of the current node, the best improvement. So we select it, and this time all these 4 are the best options. We select them, and you see we keep on doing, and finally we reach a point which is the global minimum. That's the idea. This type of method we classify them separately. We call them population based search methods. They are not local search methods. Clear? So let's see now the theory. So unlike hill climbing, here we keep track of k states rather than just one state. It starts with k randomly generated states. Okay, and at each step all the successors or the next states of all these states are generated. So you generate the next state for all the current states. If any one is a goal, so if any one is a goal by chance, the algorithm will stop. Otherwise, you will select the k best successors. So this is important step. You will select the k best options from the complete list. Complete list means, in our case here, 4 current nodes or 4 current states plus 4 next states. Total 8. Complete list means that thing. So you select them and then you repeat. So remember, important point is local beam search is not equal to or not same as running the k random restarts in parallel instead of sequence. Okay, random restarts of hill climbing, what they want to say. It is not as you are running hill climbing 4 times in parallel. Because remember, if you are running hill climbing 4 times in parallel, all of them will work separately. They don't share anything. They are separate. So if it starts in one side of the if it starts in one side of the state space, it will most probably stay over there. This one will stay at another side. So they have no feedback. Clear? Whereas in local beam search, they are connected with each other. I hope this point is clear. Very important point. So drawback of local beam search is low diversity, because you will slowly start converging to one of the points. So for example, if this was not there, let's say you had one over here node, so all of them will start converging on this thing. There is less diversity, less difference. So all of them will start converging on this point, which is not a good point. So what you can do is that, again, just like we did in hill climbing, we introduced stochastic hill climbing. We can introduce over here stochastic beam search, where you introduce a little bit of randomness in the selection of next node. Clear? Pause it and go through this concept. These are heavy concepts. Try to grasp it. Any questions, ask me. So here it is. If you see, the idea is keep the k states in the local beam search, k states instead of just one state, which was in hill climbing. Begin with k randomly generated states. K can be over here. We saw the example k equal to 4. And at each step, all the successors of all the k states are generated. You generate them, and if one of them is a goal, you stop, or else you select the next k best successors from the complete list, remember, from all the nodes, and you keep on repeating these 3 steps. So we have seen this in detail. I hope it's clear. You keep on doing until the local beam search it finishes. Let's take a break, and then we will continue next lecture with the genetic algorithms, another interesting and important topic.